Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 345, I chat with Paul Hales, founder of Pro Audio Technology, about room acoustics, speakers, and EQ curves. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CacheFly.com.
This is Home Theater Geeks with Scott Wilkinson, recorded March 16th, 2017. Episode 345, Rooms, Speakers, and EQ Curves. This episode of Home Theater Geeks is brought to you by BarkBox. BarkBox paw picks the best all-natural treats and innovative toys for your dog and ships them right to your door. To receive a free month of BarkBox with your 6 or 12-month subscription and free shipping, visit getbarkbox.com/twit. And by Zipcar. Zipcar is the largest car-sharing network in the world. To earn $25 in driving credit, visit joinzipcar.com/twit. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Paul Hales, an audio expert and founder of Professional Audio Technology, or Pro Audio Technology, I should say. Paul, welcome back to the show.
Thank you, Scott. Good to be here.
Now, those who are tuned in live at live.twit.tv can join the chat room there, or at irc.twit.tv, and you can post questions as we go, and I'll pass along as many as I can. It always helps to put my screen name, Scott Wilkinson, no dots or dashes or spaces or anything like that, in the message, anywhere in the message, and that way it shows up in a different color on my screen, and I can see it more easily. So, Paul, last time you were on was about 3.5 years ago, and too long in my opinion. I'm sorry about that, but I'm sure glad to have you back now. And
Thank you.
we're actually going to, believe it or not, we're going to sort of pick up where we left off. But before we do, I did want to kind of go over some of the basic assumptions or premises that you think about when you're thinking about designing a room. We're going to be talking about designing a room for sound and the interaction between the room and the speakers and the listener and all that kind of stuff, which is very important when thinking about putting together a room that you want to optimize for hearing good sound. So let's go over some of the fundamental principles by which that guide your work, I should say.
Okay, so I think there's a few things we can kind of agree on so that we don't have to cover them during the discussion. But one of the main things that I want to is going to be underlying everything I talk about today is the notion that the physics that dictate the radiation of sound from natural sound sources, whether it's a human being speaking or a musical instrument or a loudspeaker, the physics are the same, right? Physics doesn't discriminate between audio and between natural occurring sounds. And so we're going to apply that fundamental principle to the radiation of sound, the directivity of sound, I guess to be more precise, the frequency-dependent directivity of sound from natural sources as well as loudspeakers, how that interplays with the acoustic of the room, acoustic signature of the room. And we're going to see that it does so similarly. And as a result, I'm going to sort of put forward the idea that rooms are not the evil that maybe everybody has come to believe they are, and we actually need them to be there and want them to be there.
Well, I mean, isn't it true that some rooms are better than others depending on their dimensions? And
well, absolutely.
I wouldn't want to be in a cubic room, I think, right?
That's right. So there's certainly characteristics of the room that can make some rooms better than others. But I'm saying you probably wouldn't want to listen to your home theater in an anechoic chamber.
Ah, yes, of course.
No room or outside. I saw one YouTube clip where somebody was talking about acoustics, and he he made the comment that the sound system would sound the best outside. I'm not sure I agree with that. There is the need for some reverberant energy, both in hearing natural sounds, musical instruments, as well as hi-fi. So we'll talk about that, and we'll spend some time talking about how that interplays with the process of equalizing a system inside a room. Some of the other things is, I like to use the terminology system EQ rather than room EQ or room correction or room tuning, because I think that those phrases are a little misleading. We're not really doing anything when we're applying equalization to an audio system. We're not really changing the room at all. We're changing the signal going to the loudspeakers. And so I usually use the terminology system EQ because we're not, for example, preventing reflections. We can't, the system EQ can't stop reflections from happening. It can't change the acoustic signature of the room. It doesn't change the materials or the dimensions of the space. We're not correcting the room. We're not, again, changing the dimensional ratios or moving materials around. We're simply applying equalization to the audio signal, which then alters the response that comes out of the loudspeakers. Would you call that room compensation? Or I use the word compensation. We use calibration. Compensation is actually good. The reason why I say that is because when we do a system, we do compensate for very specific room realities, but primarily the ones we focus on initially are the ones that affect the direct sound, not the reverberant sound. So, for example, if something comes in between the loudspeaker and the listener, a perforated video screen, for example, that has a direct impact on the first arrival, the direct sound. We will definitely compensate for that. That's why compensate's a good word. And then any low frequency reinforcement caused by room loading, where you're near a corner of a room or you're near a wall, that essentially changes the direct sound as well. It's a reflected energy. The energy that otherwise would go backwards, the low frequency energy, is pushed forwards into the direct field again. And it's pushed forward so short a period in time that we just integrate it into the direct sound. And so we will compensate for that as well. After that, we'll investigate and determine whether or not we need to do compensation for room reverb and room reflections.
Okay. So as you said, system EQ can really do only one thing: change the electrical signal going to the speakers.
That's right. That's what it does.
And it can't do other things either, like discriminate the direction the sound is coming from.
That's right. So I think last time we spent some time talking about some of the challenges that an EQ scheme, whether it's manual or automated, some of the errors in the process, and one of them is that the microphone just doesn't pick up the sound the same way human beings do. I think we talked primarily about the head-related transfer function last time, which is the idea that our head interferes with the higher frequencies, and so our ears get two different amplitude responses, if you will. But microphones can't discriminate in the time domain either. So all the sound arriving at the microphone at any moment in time is just included in the measurement and shows up on the analyzer display. Human beings, though, are a bit different. We can discriminate in the time domain. In fact, we do. And in spaces that are of typical size of rooms or that we spend most of our time in, work, office, homes, we do that routinely. We focus in on the first arrival sound. We hear the reflection, but we distinguish between the two. Microphones can't do that. If I think the way it works is if the reflected energy arrives in the first couple milliseconds, then we just kind of we interpret that as one single sound. So if you were leaning up against a wall having a conversation, the reflection off the wall would happen very quickly, and we would just hear one sound. Once the delay of the reflection becomes several milliseconds, then we can start to separate it out from the direct sound. And in fact, we do. And then we focus our attention to the direct sound and kind of ignore the reflections, or at least consider them less.
Well, put them in the background of perception in a sense. I mean, the perception is there because you can immediately tell if you're in an anechoic chamber, which is a room with no reflections at all. You can definitely tell you're in there immediately. It just sounds weird.
Yeah, it's not that we're not. It's not that we're not detecting the reflection. It's that we're not really focusing on it or putting a lot of attention on it. We put our attention on the first sound. Then when you get into a large space and the reflections come late, 30 milliseconds, 40 milliseconds in a big space, then then it's an echo, and we interpret it as two separate sounds. And so, nobody really puts home theaters in gigantic rooms that have 30 millisecond delay, and we don't. And if we can help it, we don't want to sit super close to a room boundary either. One of the assumptions I want to make during our discussion is the money seat, the so-called money seat, is typically in the middle of the room, side to side, and 2/3 the way back or something like that from the front and back walls too. Sometimes you have to sit up against the back wall, and there's going to be consequences for that. We can talk about that situation. But if we make these other assumptions, then I'm suggesting that we're in that zone where we can discriminate, and we kind of routinely discriminate the direct sound from the reflected.
So speaker directivity of sound. That's one of the kind of important things that you bring into this discussion that you really want to talk about when thinking about how to design a room and how to put things together, right?
That's right. So, and this kind of came about because our speakers, as home theater speakers go, tend to have higher directivity than most. And so, the rules of system EQ inside rooms haven't applied the same way to our product. And so through just doing several different rooms and having discussions with other engineers that do this and participating in different workshops and things, have developed some new ideas about the importance of the directivity, how it relates to the way we experience sound in rooms. And we're going to talk about how the directivity of the loudspeaker combined with the acoustic signature of the room can inform the so-called target curve that we would use to try to do equalization successfully. There isn't, in my opinion, one slam dunk target curve that you can say, okay, it's a horizontal flat line for every situation, because I think anybody who's tried that realizes that doesn't sound good at all. So we're going to talk about the directivity of both loudspeakers and natural sounds, whether it's coming off of a piece of machinery or a human voice or a musical instrument, because the physical rules that dictate the directivity of the sound apply to all things, and the consequence of that is the room interplay with those sounds is the same for both the loudspeaker and the musical instrument.
And of course, a loudspeaker, doesn't have the same directivity or radiant characteristics as musical instruments, which is one reason why perhaps it's very difficult, if not impossible, to play back a sound of, say, a violin and be unable to distinguish, oh, that's a reproduction, that's coming from a speaker, versus that's coming from a real violin in the same room I'm in, right?
Yeah, that's right. And that's one of the variables we can't control, right? In the recording chain from the musical performance through the recording process to the playback system, there are lots of variables that we can't control. And one of them is the directivity of the loudspeakers will never match the directivity of the instruments or voice, because those all have their own independent directivities too, right?
Right. And so in fact, we have a couple of things to show in that regard, if you're ready to show these graphics here.
Yeah, why don't we look at the violin?
Right. Graphic. Sound radiation violin would be the first one to look at, and we'll be able to see here how the radiation pattern from a violin really changes at different frequencies. There it is. So tell us what we're looking at.
Yeah. So I'm going to try to avoid any kind of real technical stuff and keep it super common sense.
Oh,
And
you don't have to do that. We're all geeks on
really?
this
Okay.
bus.
Well, yeah, we'll geek out then a little bit. Maybe I'll geek out a little bit more. So the concept here is the directivity of a sound emitting object, whether, again, it's a violin or a loudspeaker or a person talking, is largely determined by the size of the wavelength of the sound being emitted. And so we talked last time about how once the wavelength of the sound coming to, reflecting off the wall to the side of your head, once that wavelength becomes the size of your head or smaller, your head actually blocks that sound. It reflects back off. A small tiny bit is absorbed, and that sound doesn't make it over to your opposing ear. So the size of the sound wave is a key fundamental factor in how sound is radiated. And so this graphic shows you that a violinist, the low frequencies, 200 to 400 hertz, and it says 550, are omnidirectional.
But the lower frequencies,
Yeah, the lower frequencies are long compared to the size of the instrument. And so the instrument radiates those waves pretty much omnidirectionally. And that's true of a loudspeaker too. In the low frequencies, loudspeakers are small compared to the wavelength. And so the sound comes out, wraps around the box, and it radiates spherically, omnidirectionally out of the speaker. Now, as we increase the frequency of the sound reproduced, then the physical dimensions of the loudspeaker or violin start to dictate where the sound goes. And you can see in the lower right graphic, the high frequency content coming off the violin, 2500 to 5000, that largely radiates perpendicularly off of the soundboard of the violin. So imagine the complexity in this situation, because where do you put the microphone, right?
Yeah, exactly.
So and again, we can't control that, but if somebody did put a microphone above violin, so if you've ever heard a classical recording where the microphones were hung over the orchestra, and so it is picking up a lot of that 2500 to 5000, well, the listeners in the audience don't get as much as that. Energy. And so the balance isn't really natural. When we hear violins in a concert hall, the sound is soft and silky. And even when it's loud, it maintains this sort of soft character. But when it's recorded with the microphone, above it, where it's getting excess high frequency energy, they can sound very strident and kind of steely and really not very natural or very pleasant at all. So, so the idea here is as the wavelength goes down, as the frequency goes up, the size of the sound wave starts to get smaller and smaller again. I think I used my fingers last time. The sound of 20 kilohertz is about that big.
Yeah.
The sound at 20 hertz is 50 feet long, right?
Right.
So now that those laws that dictate the directivity of the violin, fortunately for us, are the same laws that dictate the directivity of the loudspeaker. And while you're correct to point out that you're never going to have the same directivity, a speaker's not going to have the same directivity as a musical instrument, at least the way rooms deal with that information is similar, right? Which is one of the points I want to make. So, okay. So we talked about low frequencies being omnidirectional. So in the low frequency, the characteristics of room acoustics, most materials in rooms aren't very good at absorbing low frequency energy. There's just, the waves are too big and there's just too much energy there. And it's not very easy to absorb low frequency energy. Anybody who's had to try to design a bass trap or use bass traps will understand that. And so they don't. Rooms, for the most part, contain the low frequency energy that radiates omnidirectionally. There's leakage, but if you're in a concrete room, the best bass I've ever heard has always been in a basement where the walls are concrete and the floor is concrete. And
therefore they don't flex very much. They really reflect everything that comes in rather than absorbing any of that energy.
Right. It doesn't transmit any, and it doesn't absorb any by vibrating. And so the bass energy is contained. And then at high frequencies, common materials that we have in our houses actually do absorb high frequency energy. So we need to keep an eye on both of those things. The base energy tends to be contained, and the high frequency energy tends to be absorbed to some degree. And because with a loudspeaker, for example, I think one of the other assumptions we want to make here is that, this is 2017. Loudspeaker engineering has come a long way. Many companies out there are doing good work, and most people subscribe to the sort of Harman Floyd tool definition of a good loudspeaker, and meaning that it has a flat, smooth, on-axis anechoic amplitude response, a flat, smooth listening window response. If you define the listening window as an area, or sort of around the main axis. Yeah, plus or minus 10 degrees vertically and plus or minus 15 or something horizontally, that sort of zone where you'd be moving your head around. You want that to be similarly flat. And in a lot of speakers, it'll be very similar to the direct response. And then power response, which, I don't know if everybody has a kind of an understanding what that is, but if power response curve you would make that by measuring the total sound radiated at any frequency on all axes, all around. You'd have to have microphones all the way around the speaker, or you have to rotate the speaker. Right. And then you plot the total energy at all the different frequencies, and then you connect those dots together, and that's the power response. So it's a way to graphically represent the energy radiated, the total energy radiated by the speaker at those frequencies. And the idea here is you want that to be smooth, because that ultimately determines the reverberant energy in the room. That's the energy that we get back to us from the room. And that's typically going to be a downward sloping line. It's going to have more bass because we're radiating that bass. If it's flat on axis, the power response will have more bass content because the bass also goes to the back. The treble, because of the size of the speaker, we talked about directivity, is focused more towards the front. And so you're going to have that downward slope. So
in other words, when you measure the total power, the lower frequencies are going to have more of it than the upper frequencies.
That's right. Assuming a flat on-axis sound pressure level, right? So, you can think of it this way: when the speaker's making 80 dB at 50 hertz in the front of the speaker, it's pretty much making 80 dB at 50 hertz behind the speaker too.
Right.
But in the treble, if you want to look at 5 kilohertz or something, then it's making 80 dB in the front because we have a flat on-axis response, but it's going to be much, much lower. And at 20K, I mean, you're going to be
gone.
Not much. There's no 20K back there. So by virtue of that directivity, we get that downward slope. And so I want to tie this in with the fact that room response, room signature for typical North American listening rooms also has a downward sort of characteristic. And when you combine the speaker with the room, then the target curve ought to be a downward sloping curve, and we can define the best way to capture what that might be.
Okay, well, we will do that, and we'll talk about a lot more stuff here, very interesting stuff. But before we do, I would like to take a moment to thank one of our sponsors for this episode, which is BarkBox. Now, BarkBox delivers 4 to 6 natural treats and fun toys for your dog, curated around a surprise theme each month. BarkBox paw picks the best all-natural treats and innovative toys to match your dog's unique needs, including allergies and heavy chewer preferences. All edibles are made in the USA or Canada, and 100% of their products are tested on animals, their own. BarkBox is a great way to try a variety of treats and toys from local and small businesses that you may not otherwise be able to find. BarkBox also makes their own products through their Bark & Co. brand. They've shipped over 16 million toys and treats so far. Getting started is easy. Just choose your dog size, small and cute, up to 20 pounds, just right, 20 to 50 pounds, or big and bold, 50 or more pounds. Then choose a plan. 1, 6, or 12-month plans are available. And finally, get your BarkBox. BarkBox are shipped on the 15th of each month. BarkBox will keep your dog engaged, interested, and happy. If your dog doesn't like something in the BarkBox, they'll send you something else for free. Scout's honor. When your dog falls in love with something from the box, you can easily find it again on barkshop.com or the BarkBox app. And you can cancel anytime, and shipping is free in the continental United States. So give your dog the joy of 1,000,000 belly scratches. Get 1 month free and free shipping with your 6 or 12-month subscription by visiting getbarkbox.com/twit. That's getbarkbox.com/twit. And we thank BarkBox very much for their support of Home Theater Geeks. Okay, I've got a couple questions in the chat room here, Paul, so let me just pass those along. UJ is asking, is the current discussion, and I think he was talking sort of about microphones not picking things up as humans do, is that an argument for the validity of binaural recording and playback?
Well, certainly binaural can be very effective. I've heard it work extremely well, and it's kind of scary. This is a little different.
We should define it really quickly that binaural recording takes 2 microphones, places them in a dummy head with dummy ears, records the sound, and then you play that back on headphones, and it should be as if you were in that dummy head's position during the recording, with all of the head-related transfer function and difference in levels between ears depending on where the sound is coming from and so on. So I just wanted to make sure everybody understood what binaural recording was.
Sure, and I think this came up last time too. We talked about using the dummy head to be the measurement microphone for our test system, and it would be an improvement, right? Because it would pick up the sound field a lot more similarly than we do. Oh shoot, you know what? If you can talk for a minute, Scott, I got to do something real fast.
Okay.
Sorry about that.
That's okay. Anyway, meanwhile, let me address Emily Lestrange's question, which is sound waves are the same. They're the size like light waves. And the answer is yes. Light waves, sound waves, all waves have a fundamental characteristic called wavelength, which is the distance between 2 crests of the wave. As you might know, waves consists of an oscillating something. In the case of sound waves, it's oscillating air molecules. In the case of light, well, it's self-oscillating. In the 19th century and before, they used to think there was an ether pervading the universe that was the medium in which light traveled. But they have, Michelson and Morley in the late 19th century proved that to be not true. That there is no ether, and therefore light is more or less self-sustaining, self-vibrating. It's a bit odd, but in any event, but they all have a wavelength. And so as Paul was saying, sounds at 20 cycles per second or 20 hertz, the very lowest humans can hear typically, has a wavelength of 52 feet. So, the size of a house lot in LA anyway, is the wavelength of 1 cycle of 20 hertz. Whereas 20,000 hertz, which is the highest that babies can hear, I can't hear it, most of us can't, who are adults, the wavelength is like so. So there's a vast difference in wavelength. And that's what he's talking about when he's talking about the size of a wave. Light, of course, is much, much smaller. It's in the nanometer range, hundreds of nanometers. It used to be called angstroms, which are actually picometers, I think. I'm not sure about that. I'd have to go look that up. But in any event, it's mostly referred to in nanometers now. And nanometers are billionths of a meter. So super tiny. But red wavelengths, red light has a longer wavelength than blue light, because red is a lower frequency than blue. And the relationship between wavelength and frequency is directly inversely proportional. So as wavelength gets smaller, shorter, lower, frequency goes up. So that's the answer to that question. Let's see here. User 4307, my ears cut off at 17 kilohertz and I can't hear that last 3% no more. Yeah, you and me both, buddy. Any adult.
17's pretty good, actually.
Actually, 17's quite good.
Mm-hmm.
Any adult, if you can hear up to 17, you're doing really well. And if you played in loud rock bands or went to a lot of arena concerts, as Zephyr did, it's going to be probably lower than that. Let's see. User 4307 again. Mike's, well, let's see. Cardioid ones don't hear in context. No microphone hears in the same context we do. The Gem Doctor, yes. Well, light, this is interesting. Light is transmitted in a series of quantum packets called photons. Sound, as far as we know, isn't, although I wrote an April Fool's once about phonons, that is quantum particles of sound. But anyway, that's neither here nor there. I think we have Paul back here. So where were you? Where were we at?
Let me just interject and say the first rule of good system EQ is plug your computer in. So sorry about that little interruption.
That's what the problem was? Okay, all right.
Yeah, I came in, set my notebook down, and didn't plug it in, so I apologize for that.
Okay.
But where we're going with it is that typical rooms that we spend our time in have the same effect on musical sounds and people talking in them that they have on speakers, right? So when you play back an audio system inside a room, or if you played a musical instrument in the same room, the acoustic signature would interact with those two sound sources the same way. And both sound sources have not the same directivity, but they have the general directivity characteristics where low frequencies are more omnidirectional and high frequencies are more directional.
Right.
So the idea there is we tend to hear things in rooms. Now you can hear instruments outside and large concert halls, that's a little different. But in a jazz club or a coffee house or your living room or the piano bar or whatever, you're taking in these musical instrument sounds in spaces that are typical of where we spend our time. So where I'm going with this is the idea that the room's impact on the speaker, provided a good room. I mean, two of the assumptions are the room has got to be pretty decent and the speaker's got to be good. You know, this doesn't apply at the corner cases. This doesn't apply at the extreme dead room or extremely reverberant room. But in the middle, where the acoustic of the room is pretty solid, the sound signature on the speaker is there, and it doesn't necessarily have to be deleterious to the sound. In fact, I'm going to argue that it needs to be there because we experience sound in rooms all the time, and we expect it to be there. So we walk into the room. One of the things we do right away is we assess the acoustic, and then we adapt to it. I think Floyd Toole spends a lot of time talking about adaptation, and that's when we determine the time delays of the reflections and can start to focus on the main sound. And so if that's true, and we're used to that sort of low frequency containment and high frequency attenuation typical of rooms, and the directionality typical of sound emitting sources, and that they're similar, then that room signature on the speaker is okay. And in fact, good if the acoustic is good. Again, if you listen to a pair of speakers in an anechoic chamber, which would be the absence of all reflections, I don't think you would be very engaged in the sound.
No.
So taking this one step further, I can hear skeptics say, well, wait a minute, when you make a recording, the room that the recording is made in has the room signature already in there. So then if you put your speakers in a room and allow that room to have that same character where it attenuates some of the highs and it accentuates some of the lows, now you have two rooms, right? You have the double room sound.
Right.
But actually, most modern recordings, I would say, are close mic techniques where, certainly for popular music and for rock and roll, these guys are putting the mics right in the instruments.
You're not
they're
hearing
really
any of the room. They're not picking up any of the room in that case.
That's right. They're really not. The direct sound, they're so close to the instrument or the voice. When Adele sings, she's, a foot or maybe 2 feet away from the mic at the most. Mm-hmm. And, we would never, two things. One, you don't get a lot of room acoustic when you do that. The direct sound is so loud compared to the reverberant sound that you don't pick it up. And then also, it's an unnatural perspective because we would never hear Adele 2 feet from her mouth, right? We don't run up and stand 2 feet from her. So my argument is, since we anticipate the room to be there all the time, and then if the recording doesn't have it, then if you want to put that room effect back in, then what better room to put it back in than the one that you're in, right? So
true enough.
Does that make sense?
It does, except here, this brings up another question, which is, you're right that certainly pop and rock and that kind of recording is all mostly done close mic'd, as you describe. But then in the process of mixing and mastering, they will add artificial reverb to the sound because otherwise it'll sound too dry. The recording will kind of sound funky and limp and not really good. So they're going to add artificial reverb. How does that affect?
That's right. Well, and there's nothing we can do about that, right?
No.
The recording engineer can't anticipate the amount of reverb that would be best in my room and in your room, and the room can't adjust for it. And it's the artistic choice of the mixing engineer, really, at that point. And we're starting. I wanted to bring up, and we're starting to head down the rabbit hole of, I think. Floyd Toole refers to it as the circle of confusion, right? Mm-hmm. Because there's so many variables on the recording side and so many variables on the playback side and they all interrelate and they all impact the sound. And because we can't control them, it is kind of a circle of confusion. And you just brought up one element where if they add a bunch of artificial reverb, then it will come across as, in my opinion, artificial reverb. Now, immersive audio has an opportunity to actually make possible capturing real reverb. There's a recording that I use as a demo here at our experience center of a pipe organ. It's an Oro 3D recording. And so the energy of the pipes themselves is coming out from the front, coming out of the left, center, right speaker. And all of the immersive surround channels really are just reproducing the reverb captured in the cathedral that the organ was in.
In that case, you want the room sound in the recording.
Right. In that case, you're actually playing back. This is a different situation where you still have the effect of the room you're sitting in, but the recording is recorded explicitly the reverb of the cathedral. And because it's played back at a level higher than the energy you would typically, the reverb you get from your little room, the louder signal is the recorded cathedral reverb, and now you're tricked into thinking you're sitting in the cathedral. It's a great effect. It works great. You close your eyes and you listen to the whole thing, and then when you open your eyes again, it's really disconcerting to notice that these walls are really close because it gives you the sensation of being in the big space.
Mm-hmm.
But that's
somebody in the chat room asked a related question here, and I just want to sneak it in here real quick. Most AV receivers will have various DSP modes like cathedral or jazz club or something like that, where they're trying to simulate the sound of any recording being played in a cathedral or a jazz club or something or another. But I generally recommend not using them because it leads to the circle of confusion, right? Yeah, and I don't know that I've ever experienced one that I thought was particularly good. It's a neat effect, but I've never really thought it enhanced the performance. I'm kind of a purist. I believe that what we're trying to do with audio is to, as faithfully as possible, deliver what's in the recording. I think last time we talked about some of the ways you can screw up sound. Of which there are many.
Oh yeah, the surround processors are just full of ways to destroy the sound. There's compression, there's limiting, there's the processing you're talking about, there's parametric EQ, there's automated EQ schemes, there's any number of ways people could get in trouble. And I believe you make the audio components as good as you possibly can, and then try to deliver as faithfully as possible what's on the recording, what's on the movie, what's on the Blu-ray, and these features you're talking about detract from that. So I don't really support or wouldn't want to use those.
Yep. Okay, that's fine. Just wanted to get that in there. It was a comment made in the chat room. So please go right ahead.
Okay, so we've discussed that rooms tend to contain low frequency energy. So the low frequency energy that radiates to the back of the loudspeaker tends to get, for the most part, reflected back into the room. Mm-hmm. And then they always typically absorb high frequency energy just because soft materials, furniture, draperies, area rugs, people. And so since they also do that on any sound occurring in that room, and since we are in that room and we have evaluated that acoustic, I think that interplay between the directivity of the speaker and the transfer function of the room, or the acoustic signature of the room, ought to inform the target response that we seek in our equalization process, because
okay.
that's the natural response of that space. Again, if you have a bad space, then no. I mean, and
there's not much you're going to be able to do.
Exactly. EQ is not going to fix a bad room. It can't, right? So the way to fix a bad room is to address the acoustics, right? And fundamentally, that's what we encourage. Is we say, get the acoustics of the room, address the acoustics of the room in the acoustic domain, address the loudspeakers in the loudspeaker domain. And by that I mean buy good loudspeakers, and if you do both of those things, then the EQ, the system optimization, let's say, or system compensation becomes becomes much simpler, more straightforward. And this is where that natural response can kind of guide us a little bit. The automated systems, we talked about how they're blind to directivity and to the room response, and so they don't have a way to calculate an informed target that accounts for those things. And then we have the problem with the microphone sort of detecting the sound field differently. We also talked about how they don't discriminate in time. So they have all of these variables that make it challenging for a algorithm to intelligently, optimize the sound in a way that is always going to become better. Now, it's not totally true in the low frequencies. In the standing wave portion of the frequency range, so typically below 200 hertz or so, the automated systems can be helpful there on their own, because at that point, the room acoustic materials and the directivity, both of those are not a factor anymore. There is no directivity that low. That wave is 5 feet long or something like that, and so speakers are largely omnidirectional. And the standing wave mode patterns in the room take over, and the system does have knowledge of that because it's right there in the frequency response, right? So they
by the way, we have a picture to show that, called acoustic regions. Just wanted to show this. This is one of the ones we showed last time you were on. I wanted to make sure everybody saw that.
Right. So, it depends on the size and proportion of the room, but generally speaking, for most common home theater spaces, it's around 200 hertz or so, where below that frequency, the standing waves, which are determined by the proportional or the dimensional ratios of the space, they dominate the sound. They take over. And then above that frequency, it's the reflected sound, or what I'm calling the room signature or whatever, that determines the sound field. And so below and in the standing wave mode region of the frequency of the bandwidth, then the automated systems actually can be quite good, and the good ones can be very good, and I usually let them do it. But above 200, I believe that you need an educated, experienced sound engineer or acoustics person or audio professional that can factor in the realities of the acoustic space with the directivity of the speakers, and let that guide the target response. And so I have a sort of a method I use to do that. Shall I go into that? Do you want to talk about
Sure. Although before you do,
where do you want to go?
Before you do, let me just quickly say that Digmax in the chat room has said something I think that's germane here, which is, so very directional speakers aimed at the listener should reduce room impact on the sound.
That's right. That's exactly right, and it's a good time to bring this up. So,
yep.
If you measure our highly directional speakers, like if you see the speaker above my right shoulder or left, it's backwards over there, that's a 15-inch two-way with a 2-foot by 1.5-foot horn on there, and that speaker is quite directional. The horn maintains its pattern down to 500, 600 hertz, something like that.
Wow. So it's directional even down that low. That's
right. And so the way the dispersion of that speaker works is in the lowest frequencies, of course, it's omnidirectional like any other speaker. Speaker's 2 feet wide. So at about 500 hertz or so, as you go up in frequency, the omnidirectional pattern of the 15-inch woofer starts to narrow by virtue of the fact that the 15-inch woofer now is starting to become significant compared to the wavelength, right? Yeah. And it becomes more controlled right as the horn takes over. So it provides a smooth transition from omnidirectional at the lowest frequencies to handing over the sound to the horn. And it matches the directivity similarly, and then the horn maintains its pattern all the way up, essentially. So those speakers will focus the sound at the listening position and keep a lot of the sound off of the walls and the ceiling and the floor. And so when you measure that speaker in a room, and we have a measurement, we can look at it. We have the LCR speakers.
Okay, that's curves. Called high directivity, I believe. Response high directivity.
That's right.
Let's take a look at that one.
So you can see what I'm talking about. This is unequalized response of the left, center, right speaker in our listening room here, and there's a lot more energy at the low end, and then it shelves down, and right about where I said 500 hertz or so, it sort of flattens out, and that change in response there is due in part to that high directivity of the speaker and the influence of the room. Now, if we were to put a wider directivity speaker, like a normal speaker that had cone, mid-range, and dome tweeter, you wouldn't see nearly as much difference in level at 1K compared to like 100, for example. You would see a lot less. So any kind of automated system isn't going to know which speaker's there, and it's going to EQ the two very differently. And what happens with a high directivity speaker like ours is it goes, wow, look at all that mid bass and bass energy, and it either endeavors to take that away, or usually what it does is it raises up the level above 500, 4 dB or 5 dB or something.
In order to make a more flat curve all the way across the entire sonic spectrum.
That's right. And that speaker measures very flat on axis anechoically. So I have a large space here. I have a 28-foot high, very large space where I can raise the speaker up off the ground and get anechoic, quasi-anechoic measurements down to just below 100 hertz or so. And the anechoic response is super flat. So you can imagine if you raise up the response 4 dB for all frequencies above 400 or 500 hertz, now the direct sound has this shelving up of 4 or 5 dB from 400 hertz and up, and that is not a pleasant sound to listen to. So, if you believe as I do that we tend in rooms the size of our theaters, that we tend to kind of focus on the direct sound, that direct sound has now become very aggressive, very thin, very harsh, and very forward. And Inevitably, whenever I've seen an automated system EQ a high directivity speaker like that, that's what happens. And so, a qualified engineer needs to intercede and change the target curve. And this is what I'm saying is that measured sound that we just looked at, that ought to inform the target curve, because that tells you in this space what the speaker is doing, the directivity of that speaker does within the acoustic signature of this room. Now, even though I'm educated, I know the speakers very well, and I know the acoustic environment by visual inspection and just clapping and understanding it, I'm not going to be able to guess either at the best possible target curve. There's an infinite number of possible curves that are all that result from this sort of interrelation between directivity and the natural acoustic of your space. And so the way I do it is I back into it backwards. I start by taking measurements. I'll take a 2 microphone measurement, one with the microphone in the near field of the center channel, and then a microphone in the sort of money seat. And this gives me a view of sort of the more natural response of the speaker with the room effect minimized. That's the close mic measurement. And then the mic that's placed at the money seat gives me an idea of what the room does to that response as the sound bounces around and then comes to the listening position. So using knowledge of what's happening to the direct sound, meaning the screen material, if it's a perforated screen, we need to account for that. And through the near field measurement, and we have tools in our amplifiers where we've measured the different screen materials, and you can just select from a list. We've measured them in a laboratory, and we have a compensating filter, which essentially compensates for the high frequency attenuation of that material. We'll turn that on, and then we'll try to assess how much of the boundary reinforcement is affecting the bottom end, because again, that boundary reinforcement affects the direct sound. It gets folded in with such a little time delay that it basically just arrives at the listening position at the same time as the direct sound.
Which really means if you're near a boundary, or if the speaker is near a boundary, that is a wall, then the bass, the low frequencies are going to be accentuated because of that fact.
That's right. You've essentially reduced the angle at which the energy radiates, right? We talked about how it's 80 dB in the front in an anechoic chamber and 80 dB behind. Now you're forcing all that energy that would otherwise wrap around and go behind, you're forcing it back into the room. And the theoretical perfect result of that is that the sound pressure level goes up 6 dB or so. For each halving of space, each boundary. So we have in our amplifier a filter called two surfaces, where you're near two surfaces.
That is in a corner, or no, at a wall and a floor.
A wall and a floor, or a wall and another wall. Then we have one called three surfaces, which is if you for some reason had a speaker up in the corner of the room where the ceiling and the two walls came together, that would be an unfortunate situation. But if you had that, you can engage the filter. Now, it's not a slam dunk. It's not a perfect amount, but it is an amount based on theory, based on the approximate size of our speakers, and it gets you close. And then we have some other adjustments. 1 dB bass shelves and 2 dB bass shelves, where you can get any combination you want. Or for the experienced users, we have parametric EQ, where you can make a shelf filter with infinitely adjustable shelf filter. But for the guys that aren't audio engineers, we have those more generic two surfaces is plain English. They don't need to know Q or amplitude or frequency or anything.
Yeah, that's getting pretty geeky, which is fine. Listen, before we continue, and I know there's a lot more to go and we don't have all that much more time, but I do want to take a moment to thank our other sponsor for this episode, which is Zipcar. Now, Zipcar is the world's largest car-sharing network, operating in over 500 cities, towns, colleges, and more than 50 airports around the world. Zipcar provides a cost-effective alternative to car ownership. Zipsters only pay for the time they actually use a vehicle and have no responsibility for additional costs. Drive cars by the hour or by the day with gas and insurance included. With Zipcar, you'll have the freedom to choose when and where you want to drive. Zipcar's self-service vehicles are available on demand in conveniently located reserved parking spots in your neighborhood. You can reserve your Zipcar in minutes, 24 hours a day, 7 days a week, by calling or visiting the website. Simply book the vehicle of your choosing and unlock your selected vehicle with your Zip card. Zipcar offers over 50 makes and models of cars that range from environmentally friendly hybrids, EVs, and PHEVs to luxury vehicles, SUVs, pickup trucks, and cargo vans. You'll have the option to choose the make, model, type, and even color of the vehicle you want based on the needs of each trip and the available Zipcars in your area. Reserving, accessing, and using a Zipcar is as easy as getting cash from an ATM. And car sharing is good for the environment. Zipsters reduce their personal CO2 emissions by between 1,100 and 1,600 pounds per year. For wheels when you want them and $25 in driving credit, go to joinzipcar.com/twit. That's joinzipcar.com/twit. And we thank Zipcar very much for their support of Home Theater Geeks. SoCal Ray Jr. in the chat room is asking, what software are you using for the measurements we just looked at for the high directivity speakers?
Yeah, well, so the graph that you saw on the screen, that's the Trinov Altitude 32 surround sound processor graph results. You know, built into that surround sound processor is a very sophisticated acoustic analyzer that gives you tons of results, and that's where that graphic was generated. When I'm measuring within a room for my manual equalization, I use Smart, which is a PC-based. It uses the sound card, and the good thing about Smart is it allows you to have multiple microphones, and it will display the results of multiple microphones simultaneously. I don't even think there's a limit. I think you can just keep adding microphones. But I have an 8-channel roll-in interface, so I can have as many as eight microphones if I want, and that becomes very powerful because it's very difficult to place a microphone, take a measurement, and I guess you store that one, then you run over and you move it again and you do it again. It's a lot more powerful when you can see them simultaneously. And the changes you make, you get to see what happens in multiple seating positions. So
this answers Web 7413's question, which are your measurements a single mic or summing? And they are in fact summing.
Well, in this case, I get to see all the curves individually. I'm not. There's no mic matrix or anything, and there's no multiplexer, so I'm not seeing a average curve. Although I can calculate that average curve, I don't do it that way because I prefer to see the actual response at the individual locations. Rather than some average, which I can't relate to. So it would do that, but I just don't. I don't look at that information. But real quickly, let me just conclude on that because I do want to get to the X-curve
yes,
topic
that was my
possible.
Exactly. Go ahead.
Okay. So the way I back into that sort of target curve, as I mentioned, even though experienced system calibrators have a lot more information available to them than a automated algorithm would have, it's still really much impossible for us to know what the visual representation of the sound should be at the money seat, right? So I back into it by using sound as a reference. I actually just listen in stereo, and I optimize the sound of the left and right speakers playing back stereo using material I know very well. So I rely on the analyzer and knowledge to do that screen compensation and the boundary gain compensation, and then I rely on my ears after that to by trial and error to get the sound
kind of fine tune
optimized. Right, exactly. I mean, I'm very familiar with this material, and so I can very quickly assess, for example, the boundary gain. We can guess at first, and then if there's too much boundary gain in the signal, it will manifest itself as a resonant quality in the bottom end. You know, the woofer is going to be too loud, and it's going to have kind of a chesty or boxy coloration, a resonance, and I just balance that sort of low frequency energy in the shape of the low frequency response until that goes away, until I've got a clean response that preserves the timbral accuracy. So I'm a big believer in getting the speakers accurate, and when the speaker has got an accurate amplitude response, the instrumental timbre harmonic structure is correct. And so using my ears, I do that. And then once I'm convinced I've got the best sound I'm going to get, I copy those settings into the center channel, and the screen wall is essentially done at that point. But what that also gives me is an opportunity to see what that response looks like at the listening chair, right? So I've reverse engineered what the room response ought to look like to get that sound, right? If I trust my subjective judgment to do that well, right? Then now I've got a picture of what that is, and I can use that to guide me as a target. So if I wanted to do any additional EQ, I would seek to maybe smooth that response a bit, but I would not want to change the overall shape, tilt of it dramatically, because if I did so, then all that subjective evaluation, all that goodness that I got in there would go away. So I'm kind of saying the empirical experimentation derives the measured result, which then can be used as a target to do additional fine tuning. Does that make sense?
Yeah, it does. It does. Absolutely. And in fact, speaking of target curves, we wanted to make sure to talk a little bit about your ideas or your thoughts on the X curve, which is tell us first what that is, how it came about, and why you think it might need to be modified.
Yeah. So the X curve, the movie industry, God bless them, they set standards because they wanted to kind of standardize the experience everybody receives when they go to movies. They've standardized the sound and the video quality so that if you see a movie in your neighborhood and I see one in my neighborhood, we get largely the same experience. And so back in the 70s, I think is when it first started, they sought to try to find a way to normalize the sound quality from cinema to cinema. And they came up with this target curve, exactly what we're talking about, the target room response for a typical theater. They named it the X curve. There it is there. There's several of them. This is the one that was, I think, 1998. They modified it, and you can see it's sort of flat from the bass frequencies through the mid-range. Then at 2K, it slopes down at minus 3 dB per octave, and then there's another inflection point at 10K, and it slopes down 6 dB per octave from there. So that's what they've used to, when somebody goes out to calibrate a cinema and set up the sound in a cinema, they use that as their EQ target. Now, how this came about, Scott, you and I talked about this the other day, is I experienced, we sell, during a course of a year, most of our systems go into home theaters, but we always get a few DCI or digital cinema installations. They're going into houses, but they're essentially putting the commercial cinema system in their house.
These are very, very expensive houses and systems.
That is correct. And yeah, because the projector is super expensive, and they got to have the Do-Re-Mi movie server and the Dolby CP850 processor. And so when they put in a system like this, Dolby commissions it, and particular for Atmos, the Atmos specifications are pretty rigid and pretty hard to hit. I mean, they have very high expectations and demand a lot from the audio system. For example, just real quick, for the left, center, and right speakers, they want to see 105 dB at the reference listening position based on the AES power handling spec, which is a 2-hour spec. So another way to say that is they want your speaker to be able to play 105 dB, pink noise at 105 dB for 2 hours straight.
Oh, man.
So we did a big room that was 55 feet deep. and they define the reference listening position as 2/3 of the way back in the seating area in the middle.
Yeah.
So the reference listening position was like 32 or 33 feet away. And so any speaker to make 105 dB for 2 hours, 35 feet away, that's challenging.
That's a tall
we could
order.
do it. And then to make the order even taller, they want to have 3 dB of amplifier headroom. So
Jeez.
for example, in our 15-inch two-way speaker, which can hit that spec, SPL spec, it's got a 1400 watt woofer. So in order to get that sound at the reference listening position, you need 1400 watts, and 3 dB would need a 2800 watt amplifier, right? So
Jeez.
Super challenging. Nonetheless, getting back to my story is I got to sit in on a couple of these Dolby tunings of these digital cinema rooms, and I got to say the engineer was able to very quickly. There's like, I think 30 speakers in this system. He was very quickly able to go from speaker to speaker and get the response at the reference listening position. They use a matrix of 4 microphones, kind of in a diamond pattern where the money seat is. He was able to EQ them so that it matched the X curve. And I watched him, and it was very accurate. He followed that curve we just showed precisely. And when he was done, he had a trailer, or they have a recording. I want to get my hands on this. That's essentially a pink noise Atmos object, and the Atmos object just kind of flies around the room. So it's a pink noise, a ball of pink noise that kind of moves slowly around the room. Yeah. And I got to say, timbrally, and pink noise is very good at allowing you to hear subtle changes in harmonic content or spectral content. It did stay pretty darn consistent all the way around the room as it went from speaker to speaker to speaker, and as you became more and more off axis of certain speakers. So for achieving consistency, I give it super high or uniformity of timbre, I guess. I give it super high scores. However, in my sort of estimation, the sound timbrally was a bit aggressive. So while it stayed consistently aggressive all the way around the room. And then when we played the actual content, movies and Atmos trailers and things, it was really loud. And as you mentioned, Scott, at the beginning, your wife has to wear hearing protection
in the movies. Yeah.
Right, exactly. Reference level is already pretty loud. This struck me as to being much louder than reference level. And I'm not shy. I like to listen loud. So I was like, why is this so loud? And so I asked the technician, I was like, is that reference level? And he said, yep. When you set the volume knob on the Dolby processor to 7, that's supposed to be reference level. And I was like, well, yep. That sounds really loud to me. And I was measuring peaks well over 105. They were like 115. Mm-hmm. And so
you're doing the same thing I do. When I go to the movies, I take my measurement equipment and I measure. And I've had the exact same experience you have in Dolby demo theaters, where it just sounds really loud. Right. And I think we talked about this too. I also heard the Dolby Atmos room that they have in Burbank that kind of doubles as a demo facility as well as a mixing facility. And I was there with a friend of mine who's he owns a loudspeaker company in the professional business, and so he's not at all involved in cinema, but he is involved in sound reinforcement. So he's used to rock concerts, and that's what he does. And so when this demo was over, he threw up his hand and he said, are you guys playing this at any kind of predetermined level? And the presenter said, yeah, that's reference level. And I was like, wow, that seemed way louder to me than reference level. And so that started me thinking, like, why is that happening? And, I got to admit, I think there is probably some commercialization of trailers and things. They make them a little loud on purpose for marketing reasons, and that's fine. That's certainly within their right to do that. But this seemed louder than that even to me. Excessive,
and
shall we say.
Yeah. And so after putting two and two together of that experience, together with the timbre didn't seem quite right. Like, we have a 23-channel Atmos system in the room I'm in right now. And when we play the Dolby trailer, for example, that has a lot of wind in it, the leaf trailer, and there's wind blowing around and leaves and stuff, the character of the sound of the wind and the leaves is soft. Wind is, it's not a harsh kind of sound. But in those trailers, in the rooms that were optimized to the X curve, took on a very aggressive sort of quality to the sound of wind. It was like, it was, and the leaves, it took on an unnatural quality. It reminded me of PA speakers playing the sound of leaves and wind. I just heard horns. I just heard, compression drivers blasting a kind of a nasty version of wind at me. And I didn't understand where that was coming from. So that started me thinking. So now we're going to tie it all together. Right. Good. So anybody who got bored a long time ago and left, they're going to miss out on the best part. But so
and that's good because we're a little over time here. So let's.
Okay. So I'll try to go fast. So we talked about how rooms reinforce the low frequency energy and they suck out the treble energy. So the X curve in the top end has got the right idea. It's showing the typical absorption you might have, and it rolls off. I think it might actually, in my opinion, do a little bit too much of that. But in the bottom end, you'll notice that it's flat. So there isn't any allowance there for the kind of bass gain that you would typically get from a room. Whether it's a musical instrument or a speaker or whatever. And when you do that, so you set the meter to 85 dB, and that's how they set the level for that channel to determine that when they play it back at reference level, that the average is going to be 85 dB. So if we look at the next one where it shows my suggested modification. So for medium and small rooms, this wouldn't really apply as directly in giant rooms, but for rooms that are sort of medium size. Scott, do you have a feel for how many seats are in that Dolby Burbank facility? Is that
that Burbank facility probably has 20 or 30 seats.
Is that all? Is it that small?
Yeah. Well, it might be 35. I don't know. It's not very many.
Okay.
Maybe 35 or 40. Let's say that.
Okay, so certainly in a room
because there is a big mixer in the middle of it.
Yeah, it's a giant mixer, and seems like the rows. But anyway, so in a room about that size, kind of a medium or a small commercial cinema, and in particular in small home theaters, that gently rising mid bass and elevated low frequency tends to provide the most accurate timbre in my experience. And in fact, anybody who's taken a speaker that measures flat anechoically, if you get a well-engineered speaker, say, something from Harman or Revel, where they follow that principle pretty closely, you're going to see that. You're going to see some elevation in the bass area relative to sort of the mid-range. So let's define the zones real fast. I like to think of the bass as 100 hertz and down. Mid-range is 100 to 500. And Siri just thought I talked to her. At 500 to 2K is the mid-range, and then 2K and above is what we'd call treble. So if we make this modification that I'm suggesting, if we go to the next slide, when you EQ for 85 dB average SPL at the reference listening position, that extra energy in the low end is going to push the whole curve down when you read 85 dB on the meter, right? The way the meter works is it just takes all the sound at all frequencies and lumps it together and calculates one pressure. So the additional energy in the bottom at 85 dB will push that whole curve down.
The mid-range and the upper.
That's right. So two things happen. One is the mid-range at reference level will be in an absolute basis lower, right? So it's not going to seem as loud to us. It's going to be a few dB less loud. And then the other thing is when you get more mid-bass and low-frequency energy into the spectrum, and it psychoacoustically, it de-emphasizes the mid-range. So the X curve as it is, you end up with an emphasized mid-range because you're taking the top out and you haven't allowed for the natural sort of rise in the bottom that you would get from a typical enclosed space. And to my ears, both the pink noise and just the content sounds too mid-rangey, right? So I'm saying the reason, Scott, why you and I reacted that way was because it was too loud. It wasn't, the mid-range level relative to 85 dB because of the target shape. It had too much mid-range content in it. And you'll see at the right there, I had hint. I'm showing a slightly lower roll off in the top end. I think that the X curve is maybe a bit too much. You don't get a lot of top end in a commercial cinema, and compression drivers and horns are better these days than they were 20 years ago, and so you can get some top octave out of those drivers now. If you increase the highest frequencies, that tends to soften the sound too. So
if you don't do it too much.
Right. Yeah. You can't turn it up too much, but in the top end, and I only cross the X curve there at 10K. We're talking about the top octave mostly. As long as you're not making a bump, but you're just kind of smoothly increasing the energy, it will also serve to kind of soften up the sound. You can't have a peak in there, but if you have a bit more top end, it will soften up the sound too. And so our speakers would tend to follow that red line. And most listeners that come through here, one of the comments they make is, wow, that was crazy loud, but not at all sort of harsh or fatiguing. It's able to be loud without seeming overly loud or obnoxious like the sort of the X curve provides. So that's my 2 cents. If anybody out there at SMPTE is listening, give me a call. Let's talk about this. I could be wrong. I'm willing to explore that and see if there's any merit to what I say or not. But that's kind of what I wanted to get off my chest this time.
Well, that's good, and I really appreciate you doing that. That makes a lot of sense to me, and I will be very interested to hear what others in the industry have to say about it. We're going to have you come back because we didn't even get to Dolby Atmos and immersive audio, which is definitely something that you've got a lot to say about as well. So will you come back and talk with us again?
Yeah, absolutely. It's fun. I like to geek out.
Yeah, me too. That's why I do this show. Yeah. Thank you so much. That's Paul Hales, founder of Pro Audio Technology, makers of fabulous speakers, by the way. I have heard many demos of these speakers, and they are really, really good. And his website is professionalhomecinema.com. Paul, thanks so much for being here again.
Thank you, Scott.
You can always find me at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott and at avsforum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/htg and on our YouTube channel, youtube.com/twit-home-theater-geeks. Next week, my guest geek is scheduled to be Ralph Potts, the Blu-ray and now Ultra HD Blu-ray reviewer on AVS Forum. And we're going to be talking about our favorite movies and the best movies to show off certain aspects of your home theater, high dynamic range, immersive sound. So let's get our Blu-ray geek on next week, shall we? I do hope you will join me. Until then, geek out.